Tonight, everything you believe about empty space is about to be challenged. It sounds impossible because the idea feels too simple to be wrong. Between the stars, there is nothing. Between galaxies, there is nothing. Beyond the reach of light lies an endless silent void where absolutely nothing exists. For centuries, that wasn't just common sense, it was science. If you remove every planet, every star, every atom, every particle of dust, and every beam of light, what could possibly remain? The answer seemed so obvious that no one thought it deserved another question. Nothing remains. End of the story. But history has taught us something deeply uncomfortable. The universe has a habit of waiting until we're absolutely certain, before proving us completely wrong. The Earth wasn't the center of creation. Time wasn't absolute. Gravity wasn't a mysterious force pulling objects through space in the way we imagined. And today, modern physics is forcing us to question something even more fundamental. What if empty space has never been empty at all? To understand why that single question matters, we first need to understand just how much of the universe it affects. Every mountain on Earth, every ocean, every planet, every moon, every asteroid, every star, every nebula, every black hole, and every galaxy you've ever seen occupies only a tiny fraction of reality. Almost everything else is what we casually dismiss as empty space. The distance between the Earth and the Moon is almost entirely emptiness. The journey from our Sun to the nearest star crosses more than 4 light-years of apparent nothingness. Between galaxies, those silent regions stretch for millions of light-years, forming vast oceans of darkness that dwarf every visible object in existence. In other words, the overwhelming majority of the universe isn't made of matter. It's made of what appears to be its complete absence, which means if we've misunderstood empty space, we've misunderstood the environment that makes up almost the entire universe. For generations, even physicists believed the mystery had already been solved. Empty space wasn't expected to do anything because, by definition, it contained nothing capable of doing anything. It was simply the stage upon which the universe performed its grand cosmic story. Then, as instruments became more precise, something unexpected happened. Experiments began revealing tiny effects where no effects should have existed. Measurements refused to behave the way perfect emptiness was supposed to behave. The equations describing reality kept pointing toward the same disturbing possibility, even when scientists wished they wouldn't. At first, many assumed the mathematics had to be wrong. It was easier to doubt the equations than to abandon one of the oldest assumptions in science. But the evidence refused to disappear. Every new clue pointed back to the same impossible conclusion. The vacuum wasn't behaving like nothing. Now imagine performing the simplest experiment you can think of. Remove every atom from a region of space. Then remove every molecule, every grain of dust, every photon of light, and every particle that can possibly be detected. Strip away absolutely everything until common sense tells you there is nothing left. According to modern physics, that still isn't nothing. Somehow, even after everything that can be removed is gone, reality refuses to become perfectly empty. Scientists have spent decades trying to understand why, and the deeper they looked, the stranger the mystery became. It was no longer just a question about the vacuum between distant stars. It had become a question about reality itself. If perfect emptiness cannot exist, then nothing isn't simply missing from the universe. It may never have existed in the first place. That realization transformed one of the simplest ideas in science into one of its greatest unsolved mysteries. Suddenly, empty space was no longer just the darkness separating stars and galaxies. It became an active part of the universe, something that might influence the birth of stars, the evolution of galaxies, the behavior of black holes, and perhaps even the expansion of the cosmos itself. But before we can explore quantum fluctuations, invisible fields, vacuum energy, or the astonishing discoveries that continue to challenge modern physics, we have to answer a question so deceptively simple that humanity believed it had solved it thousands of years ago. What exactly is nothing? At first, the question sounds almost too simple to matter. What is nothing? Most of us would answer it without hesitation. Nothing is exactly what remains when everything else is gone. Remove every object, every particle, every source of light, and every trace of matter, and whatever is left must be nothing. It feels like the kind of idea a child could understand. In fact, for most of human history, that definition seemed perfectly reasonable. Philosophers debated it, scientists accepted it, and generations of thinkers built their understanding of reality upon it. Empty space wasn't mysterious because it wasn't expected to contain anything at all. It was simply the absence of existence itself. The case appeared closed long before modern physics was even born. But some of the most important discoveries in science begin the moment an obvious answer stops making sense. As the 20th century began, physicists found themselves exploring a world no human being had ever experienced directly. They weren't studying planets or galaxies anymore. They were studying reality at its smallest scales, where atoms gave way to electrons, electrons revealed deeper structures, and the familiar laws of everyday life began to fall apart. The deeper they looked, the stranger the universe became. Light behaved like both a wave and a particle. Matter refused to follow common sense. Events that seemed impossible in the ordinary world suddenly became part of the mathematical language describing nature itself. Then, almost unexpectedly, this revolution reached something that had always been taken for granted, the empty vacuum between objects. Scientists expected it to be the simplest thing in existence. Instead, it became one of the most difficult things to explain. The first clues didn't come from dramatic observations deep in space. They emerged quietly from equations. Again and again, different branches of physics kept arriving at the same uncomfortable implication. A perfect vacuum wasn't behaving like perfect nothingness. It was as though reality itself refused to remain completely still. At first, many physicists suspected they had made a mistake. Extraordinary claims demand extraordinary evidence, and the idea that empty space possessed hidden activity sounded almost absurd. Yet every attempt to resolve the contradiction created an even bigger problem. The mathematics remained consistent. Independent theories pointed toward the same conclusion. Experiments began hinting that those impossible predictions might not be mathematical illusions after all. Instead of eliminating the mystery, every new discovery only made it harder to ignore. Imagine standing in the darkest place you can possibly conceive, where every star has vanished, every atom has been removed, and every source of light has disappeared. Common sense says you've reached the closest thing the universe has to absolute nothingness. Modern physics says you've only reached the beginning of the mystery. That silent darkness may still contain invisible fields, restless energy, and processes unfolding far beyond the limits of human perception. Not because scientists wanted the universe to behave that way, but because the evidence kept pointing there whether they liked it or not. And that realization changed everything. Because once the vacuum stopped being empty, physicists were forced to ask an even more unsettling question. If nothing isn't truly nothing, then what is it actually made of? The strange thing about the greatest mysteries in science is that they rarely begin as mysteries. More often, they begin as answers everyone believes are already correct. That was exactly the case with nothing. Long before telescopes revealed distant galaxies or microscopes uncovered the hidden world of atoms, humanity believed it already understood what empty space was. The definition seemed effortless. If something existed, it occupied space. If it didn't exist, then space was empty. No matter, no light, no substance, nothing. It was such a simple idea that almost no one thought it needed to be questioned. And that may have been one of the longest-lasting mistakes in human history. For centuries, philosophers argued over a question that sounded deceptively simple. Can absolute emptiness actually exist? Some believed a true void was essential because without empty space, nothing could move. Others reached the opposite conclusion. They argued that nature could never contain perfect nothingness because nothing couldn't possess any properties at all. The debate continued for generations, producing brilliant arguments but no definitive answers. Not because people lacked intelligence, but because they lacked something far more important. They had no way to test reality itself. The universe remained silent, and for nearly 2,000 years, silence was mistaken for proof. Then science changed the rules of the game. Instead of asking what sounded logical, scientists began asking what could actually be measured. That shift quietly transformed humanity's understanding of reality. One by one, ideas that had survived for centuries began to collapse under experimental evidence. The Earth was no longer the center of the cosmos. Time itself could stretch and slow. Space was no longer an unchanging stage. Again and again, the universe demonstrated that common sense was an unreliable guide to reality. Yet one ancient assumption somehow escaped untouched. Everyone still believed empty space was simply empty. Looking back, that confidence is almost surprising. Physicists spent decades studying stars, gravity, electricity, atoms, and light, while the vast darkness between those objects received remarkably little attention. The vacuum was treated as a passive background, not an active part of nature. But hidden inside that assumption was a question no one had seriously explored. What if the emptiness between objects wasn't actually empty? It sounded absurd. If there was no matter, no light, and no detectable particles, what else could possibly remain? For generations, there seemed to be no reason to ask. Then, as physics entered the microscopic world, reality began giving an answer no one expected. That answer didn't arrive through philosophy, intuition, or imagination. It emerged from equations, then experiments, and finally from discoveries that forced physicists to rethink one of humanity's oldest assumptions. The closer science came to creating perfect emptiness, the more impossible perfect emptiness appeared to become. The question was no longer whether nothing existed. The question had become why nature seemed determined to prevent it. And to understand that extraordinary shift, we have to enter the strangest domain ever explored by science, the quantum world. The deeper physicists explored reality, the less reality behaved the way anyone expected. For centuries, the universe had appeared calm, predictable, and almost mechanical. Every event seemed to have a clear cause. Every object occupied a definite place, and empty space was simply empty. It was the one assumption no one felt compelled to question. Then the quantum world opened, and that certainty began to collapse. At first, the discoveries seemed completely unrelated. Light refused to behave like light was supposed to behave. In some experiments, it acted like a continuous wave. In others, it behaved as though it were made of individual particles. Electrons proved even stranger. Instead of following precise paths around an atom, they could only be described as probabilities until they were measured. One impossible discovery followed another, and each forced physicists to accept a painful reality. The universe wasn't becoming more intuitive as they learned more about it. It was becoming less intuitive. Every answer uncovered a deeper mystery, and without realizing it, scientists were moving toward the biggest surprise of all. Then something happened that almost no one expected. The equations describing this bizarre quantum world kept producing the same impossible result. No matter how carefully researchers removed matter, radiation, or detectable particles from a region of space, the mathematics refused to describe that region as truly empty. At first, many physicists assumed the calculations had to be incomplete. They checked them again and again. Different researchers approached the problem using different methods, yet the same conclusion kept returning. The universe behaved as though perfect emptiness simply didn't exist. That idea sounded so absurd that many scientists resisted it. After all, how could nothing contain anything? It wasn't just difficult to accept, it seemed to contradict logic itself. But the deeper physicists investigated, the more the evidence refused to cooperate with common sense. Independent theories, built to explain completely different parts of nature, all pointed toward the same unsettling possibility. Something invisible remained, even after everything that could be removed had been removed. The mystery was no longer philosophical. It had become physical. And that changed the stakes completely. If the vacuum wasn't merely an empty container, then it wasn't just the background of the universe. It was part of the universe itself. Every star that burns, every galaxy that evolves, every black hole that bends spacetime, and every atom in your own body exists within this invisible framework. If physicists misunderstood the vacuum, then they may have misunderstood one of the foundations upon which reality itself is built. The emptiness surrounding everything was beginning to look less like a void, and more like an active participant in the cosmos. But an even greater mystery was waiting. Discovering that empty space wasn't truly empty only created a far more difficult question. What exactly was still there? If it wasn't ordinary matter, wasn't light, and wasn't any familiar substance, then what was filling the vacuum? The answer would force physics to abandon the centuries-old picture of a universe made primarily of particles. Instead, scientists would begin to describe reality as something far stranger, an invisible ocean of fields extending throughout the entire cosmos. And once that idea emerged, the meaning of nothing would never be the same again. Bill Cull. Hum documentary ki pale major scientific payoff para gahain. Tak viewer ni surf itna sika haikai nothing, shayad exist na haikarti. Section 3 ka kam haya sawal ka pale real answer dina, quantum fields. Is section mi sabs bada challenge haikai concept, co-simplify karna hai bina, oversimplify kea. Viewer co-science samaj by or mystery by zinda ra. If empty space isn't truly empty, then something must be taking its place. For decades, that question haunted some of the greatest minds in physics. What could possibly remain after every particle had been removed? It wasn't an ordinary substance. It wasn't invisible dust drifting through the cosmos. It wasn't undetected gas hiding between the stars. Whatever it was, it had to exist everywhere at once, even inside regions we had always called empty. The answer that eventually emerged was so unfamiliar that it forced physicists to rethink what the universe is actually made of. Most of us grow up believing that reality is built like a giant collection of tiny objects. Everything around us, trees, mountains, planets, stars, even our own bodies, is made of smaller and smaller particles. Reduce matter far enough and you eventually arrive at the fundamental building blocks of nature. It seems like a perfectly reasonable picture of reality. For generations, scientists believed it too, but as quantum physics matured, that picture began to change. Surprisingly, the deepest layer of reality didn't appear to consist of particles alone. Instead, particles began looking like something else entirely. Imagine standing on the shore of a perfectly calm ocean. From a distance, the surface appears flat and motionless. Then a wave rises, travels across the water and disappears. The wave feels like a separate object, yet it isn't something independent floating on top of the ocean. It is simply the ocean behaving in a particular way. Remove the ocean and the wave cannot exist. Modern physics suggests that particles behave in a remarkably similar fashion. An electron isn't necessarily a tiny ball moving through empty space. A photon isn't merely a microscopic packet racing across the universe. According to our best theories, these familiar particles are better understood as tiny disturbances, localized ripples, in invisible quantum fields that fill the entire cosmos. That idea changes almost everything. It means the universe isn't mostly empty with occasional particles drifting through it. Instead, the universe may be completely filled with fundamental fields, while the particles we observe are only brief excitations appearing within those fields. In other words, what we call an electron is the electron field vibrating in a specific way. What we call a photon is the electromagnetic field briefly disturbed. Different particles correspond to different underlying fields, each extending throughout the entire universe without interruption. Even the emptiest region between distant galaxies isn't free from them. The fields remain, whether particles are present or not. At first glance, this might sound like little more than a clever mathematical description. But over the past century, quantum field theory has become one of the most successful scientific frameworks ever developed. Its predictions have been tested with astonishing precision, explaining countless experiments with an accuracy unmatched by almost any other theory in science. And hidden within that extraordinary success lies a breathtaking implication. If these invisible fields never disappear, then empty space has never truly been empty. What we have been calling nothing may actually be the quietest possible state of something that fills the entire universe. But that realization creates an even deeper mystery. If these fields are always present, even inside a perfect vacuum, are they ever completely still, or is something happening within them? Even when the universe appears perfectly silent, the answer would reveal one of the strangest behaviors ever discovered in nature, and it would force physicists to accept that even the emptiest regions of space are far more alive than anyone had imagined. If quantum fields exist everywhere, then an obvious question immediately follows. What happens to those fields when nothing appears to be happening? Imagine the emptiest region of space you can possibly conceive. No stars, no planets, no light, no atoms, no radiation, no detectable particles of any kind. Common sense tells us that such a place should be perfectly calm. If nothing is there, then nothing should move, nothing should change, nothing should happen. But quantum physics reaches a conclusion that seems almost impossible to accept. Perfect stillness may be forbidden by nature itself. This strange idea doesn't emerge from imagination or philosophical speculation. It emerges from the mathematical foundations of quantum theory. At the smallest scales of reality, nature no longer allows every property to be known with perfect certainty at the same time. Instead, the universe contains an unavoidable degree of uncertainty built into its very fabric. This isn't uncertainty caused by imperfect instruments or incomplete knowledge. Even with infinitely precise technology, that uncertainty would remain. According to modern physics, it is woven into reality itself. The consequences are extraordinary. If a quantum field could become perfectly motionless, its energy and its behavior would have to be known with absolute precision. But quantum theory tells us that such perfect certainty can never exist. The fields filling the universe must always retain the slightest amount of restless activity, not because something is disturbing them from the outside, but because complete stillness would violate the fundamental rules governing the quantum world. In a sense, the vacuum is never asleep. It is only unimaginably quiet. That single realization transformed the scientific meaning of empty space. The vacuum was no longer viewed as a featureless void waiting for matter to pass through it. Instead, it became the lowest possible energy state of fields that continue to exist even when no particles are present. Physicists call this the vacuum state, but the name can be misleading. It doesn't describe absolute nothingness. It describes the calmest condition the quantum fields are capable of reaching, and even that calmness is never perfect. Beneath the apparent silence, an invisible restlessness always remains. For decades, this idea seemed almost too strange to be real. How could something that appears completely empty still possess activity? How could invisible fields continue to fluctuate when every particle had been removed? Yet as experiments became more sophisticated, physicists began finding subtle evidence that the vacuum wasn't as silent as it appeared. Tiny effects emerged that could only be explained if empty space possessed properties of its own. The impossible was slowly becoming measurable. And that was the moment the mystery became even more astonishing. Because if the vacuum is never completely still, then those tiny fluctuations are not meaningless background noise. Under the right conditions, they can briefly give rise to phenomena so bizarre that they seem to violate common sense itself. Particles can appear where moments earlier there was apparently nothing at all. For decades, this sounded like science fiction. Today, it stands as one of the most fascinating predictions of quantum physics. And to understand how that can happen, we have to explore one of the most misunderstood ideas in modern science: quantum fluctuations. For centuries, people imagined empty space as the closest thing the universe had to absolute silence. It seemed like the one place where nothing could possibly happen. No matter meant no activity. No particles meant no motion. No energy meant no change. The vacuum appeared to be nature's ultimate state of stillness. But quantum physics paints a picture that is almost the exact opposite. According to quantum field theory, every field filling the universe is constantly subject to tiny, unavoidable variations. These aren't violent disturbances or dramatic explosions unfolding across space. They are unimaginably small, occurring on scales so tiny that they remain completely invisible to human experience. Yet despite their size, they are fundamental. They cannot be switched off. They cannot be eliminated. Even if the entire universe could somehow be stripped of every particle, every atom, and every photon, these microscopic fluctuations would still remain. They are not imperfections in the vacuum. They are part of what the vacuum is. One way to understand this is to think of a perfectly calm ocean. From high above, the surface may appear completely smooth. But as you move closer, tiny ripples become visible, rising and fading almost instantly. The ocean never becomes perfectly motionless because countless microscopic movements are always taking place beneath the surface. The quantum vacuum behaves in a surprisingly similar way. From our everyday perspective, empty space appears silent and inactive. Yet at the deepest level, the fields filling the universe are constantly experiencing minute fluctuations that briefly disturb their lowest energy state. The calmness is real, but it is never absolute. For a long time, many physicists struggled with this idea because it challenged one of the oldest assumptions in science. If empty space is always fluctuating, then nothing is no longer the absence of all activity. Instead, it becomes a dynamic environment governed by the strange rules of quantum mechanics. The vacuum is not a frozen void waiting for something to happen. It is an active foundation upon which everything else in the universe exists. The silence itself has structure. At first, these fluctuations seemed like little more than an unavoidable consequence of the mathematics. They were interesting, but they appeared impossible to observe directly. Many assumed they would remain forever hidden beneath the surface of reality. Then experiments began revealing subtle effects that shouldn't have existed if empty space were truly empty. Once again, nature refused to behave the way common sense predicted. The vacuum wasn't merely described by strange equations. It was leaving fingerprints behind. Those fingerprints would eventually become some of the strongest evidence that empty space possesses physical properties of its own. They hinted that the vacuum wasn't simply a passive backdrop, but an active participant in the universe. And hidden within those tiny fluctuations was an even stranger possibility, one so counterintuitive that even many physicists found it difficult to explain without being misunderstood. Under the right conditions, the restless vacuum could briefly produce what appeared to be particles emerging from empty space itself. And that is where the story becomes truly astonishing. If someone told you that particles can appear out of empty space, your first reaction would probably be disbelief. It sounds like a claim that violates one of the most fundamental principles of physics. Matter cannot simply emerge from nowhere. Every effect must have a cause. Every particle must come from something. For generations, those assumptions seemed unshakable. Yet the quantum vacuum appears to challenge them in one of the most surprising ways ever discovered. The key is understanding what physicists actually mean when they describe the vacuum as active. They are not suggesting that ordinary matter is constantly materializing around us. Walk into an empty room and you won't see atoms suddenly appearing in front of your eyes. The phenomenon is far subtler than that. At unimaginably small scales, the quantum fields filling space are continuously fluctuating. Most of these fluctuations are so brief that they never become stable, observable particles. They emerge and disappear so quickly that the universe seems perfectly calm from our perspective. The activity is real, but it exists at the very edge of what reality allows. To describe this behavior, physicists use the term virtual particles. Unfortunately, the name has led to decades of confusion. Virtual particles are not tiny invisible objects flying around the universe waiting to be discovered. They are better understood as temporary disturbances that appear naturally within the mathematics of quantum field theory when fields interact. They help explain why the vacuum behaves the way it does and why certain measurable phenomena occur, even when no ordinary particles are present. In other words, they are not evidence that the laws of physics have been broken. They are evidence that those laws are far stranger than human intuition ever imagined. For many years, critics argued that virtual particles were nothing more than mathematical bookkeeping, useful for calculations but not physically meaningful. It was a reasonable criticism. After all, if something cannot be observed directly, how can we claim it has any connection to reality? But physics has an unusual way of answering difficult questions. Rather than asking whether something can be seen, it asks whether its effects can be measured. And in case after case, experiments began revealing tiny signatures that matched the predictions of quantum field theory with extraordinary precision. The invisible activity of the vacuum was influencing the observable world. One of the most remarkable examples occurs when two perfectly smooth metal plates are placed incredibly close together inside a vacuum. Classical physics predicts almost nothing should happen, yet a tiny force pushes the plates toward each other, as though empty space itself were exerting pressure. This phenomenon, known as the Casimir effect, is one of the clearest demonstrations that the vacuum is not an inert void. Something about empty space changes when the fields inside it are constrained. The effect is extraordinarily small, but it is measurable, and its existence tells us that the vacuum possesses physical properties that cannot be ignored. That discovery transformed an abstract mathematical idea into something much more profound. Empty space was no longer just the absence of matter. It had become a measurable component of reality. The vacuum could influence physical objects, alter measurable forces, and shape the behavior of the universe itself. But an even bigger mystery remained unsolved. If the vacuum contains energy even when it appears completely empty, where does that energy come from? And more importantly, could that invisible energy be powerful enough to influence the evolution of the entire cosmos? That question leads directly to one of the greatest unsolved problems in modern physics, and one of the most astonishing discoveries ever made about our universe. The moment physicists accepted that empty space wasn't truly empty, another question became impossible to ignore. If the vacuum contains quantum fields that never become completely still, then those fields must always possess at least a tiny amount of energy. But how much? At first, the answer didn't seem especially important. The fluctuations of the quantum vacuum occur on unimaginably small scales, far beyond anything we notice in everyday life. It was easy to assume their energy would be equally insignificant. That assumption turned out to be one of the greatest miscalculations in the history of physics. Every quantum field has a lowest possible energy state. Physicists sometimes call this its ground state, but lowest does not mean zero. Because the fields can never become perfectly motionless, a small amount of energy always remains. This residual energy is known as vacuum energy. It cannot be extracted by simply removing particles, because it doesn't belong to the particles in the first place. It belongs to the fields that continue filling space, even when every observable particle has disappeared. In other words, what appears to be empty space still carries an invisible reservoir of energy woven into the fabric of reality itself. At first, this sounded like an elegant theoretical insight, interesting, but perhaps impossible to verify. Then the calculations became deeply unsettling. When physicists estimated the amount of vacuum energy predicted by quantum field theory, the numbers refused to stay small. Depending on how the calculation was performed, the predicted energy density of empty space became staggeringly large, so large that if taken at face value, it would overwhelm the universe itself. Galaxies would never have formed. Stars would never have condensed from clouds of gas. Matter as we know it would have been torn apart long before planets or life could ever exist. Clearly, something wasn't adding up. This wasn't a minor discrepancy or a rounding error. It was one of the largest disagreements between theory and observation ever encountered in science. On one side stood quantum field theory, one of the most accurate scientific frameworks ever created. On the other stood the universe we actually observe through telescopes, a universe filled with galaxies, stars, planets, and billions of years of cosmic history. Both appeared to be correct, yet when their predictions were compared, they seemed almost impossible to reconcile. Somewhere hidden beneath these extraordinary successes was an equally extraordinary contradiction. For decades, physicists have wrestled with this puzzle. Was there an unknown mechanism canceling most of the vacuum's energy? Had the calculations been interpreted incorrectly? Or was nature hiding a deeper principle that no one had yet discovered? Despite generations of research, no answer has achieved universal acceptance. Even today, this mystery remains one of the greatest unsolved problems in theoretical physics, reminding us that the emptiness surrounding every galaxy may still conceal secrets beyond our current understanding. And then, just when the mystery seemed impossible to deepen, the universe delivered another shock. In the late 20th century, astronomers made an observation that suggested empty space might not simply contain energy, it might be using that energy to shape the fate of the entire cosmos. The expansion of the universe wasn't slowing down, it was speeding up. And suddenly, the vacuum between galaxies was no longer a curiosity of quantum theory. It had become a possible driver of cosmic evolution itself. For most of the 20th century, astronomers believed they understood the future of the universe. Ever since the Big Bang, space had been expanding, carrying galaxies farther and farther apart. The only real question was how quickly that expansion would slow down. Gravity seemed destined to win. Every galaxy pulled on every other galaxy, and over billions of years, that immense gravitational attraction should gradually reduce the expansion of the cosmos. Whether the universe eventually collapsed back on itself, or continued expanding forever at an ever-decreasing rate, was still uncertain. But almost everyone agreed on one thing: the expansion should be slowing down. Then, during the 1990s, astronomers made a discovery that completely overturned that expectation. By studying the light from extremely distant exploding stars, they were able to look billions of years into the universe's past. The observations were expected to reveal a younger cosmos expanding more rapidly than it does today. Instead, the data pointed towards something astonishing. The expansion of the universe wasn't gradually losing speed, it had begun accelerating. That single observation sent shockwaves through cosmology. Somewhere across the vast emptiness separating galaxies, something appeared to be pushing space itself outward, overcoming gravity on the largest scales imaginable. It wasn't an explosion. It wasn't the force from distant galaxies. It wasn't anything predicted by the traditional picture of a universe filled only with matter and radiation. Whatever was driving this acceleration seemed to be woven into space itself. For the second time in this documentary, empty space had refused to behave like emptiness. Physicists searched for explanations, but every possibility led back to the same unsettling idea. If the vacuum truly possesses energy, then according to modern physics, that energy should have gravitational effects of its own. Unlike ordinary matter, which pulls objects together, vacuum energy can produce the opposite effect on the largest cosmic scales. Instead of slowing the expansion of the universe, it can cause the fabric of space itself to expand faster over time. Suddenly, an idea that once seemed like an obscure consequence of quantum theory was being considered as a possible explanation for one of the greatest discoveries in modern astronomy. Today, scientists often describe this mysterious influence using the name dark energy. The label sounds dramatic, but it can also be misleading. It doesn't explain what dark energy actually is. It simply gives a name to the unknown cause behind the accelerating expansion of the universe. Whether dark energy is truly the energy of the vacuum, something entirely different, or evidence that our understanding of gravity is incomplete remains one of the biggest unanswered questions in science. Despite decades of research, no explanation has been confirmed. Think about what that means. The vast darkness between galaxies, the emptiness our ancestors dismissed as nothing, may contain enough influence to determine the ultimate fate of the cosmos. The largest structures in existence could be evolving not because of the galaxies we see, but because of something invisible filling the space between them. The vacuum is no longer just part of the universe. It may be one of the forces shaping its future. But perhaps the most unsettling implication is still ahead. Everything we've explored so far suggests that empty space is active, energetic, and deeply woven into the structure of reality. Yet one question refuses to disappear. Why do these quantum fields exist at all? Are they the deepest layer of reality? Or are they themselves emerging from something even more fundamental? That question takes us beyond established physics and to the edge of what science can currently explain. And it is there that the true mystery of empty space begins. For years, many physicists treated the strange behavior of the quantum vacuum with cautious skepticism. The mathematics was undeniably powerful. It explained countless experiments with extraordinary accuracy, yet its conclusions often felt deeply counterintuitive. A vacuum that wasn't truly empty, invisible fields filling all of space, constant fluctuations occurring even in perfect darkness. These ideas worked beautifully on paper, but there remained a difficult question. Did they describe reality, or were they simply useful mathematical tricks? That distinction mattered more than it might seem. Throughout the history of science, elegant equations have sometimes led researchers down the wrong path. Mathematics can reveal profound truths about nature, but it can also produce solutions that exist only within the equations themselves. Physicists knew they couldn't simply trust a theory because it was beautiful or internally consistent. The universe doesn't care whether an idea feels elegant. It cares only whether that idea matches reality, and the only way to find out was through experiment. The challenge was enormous. How do you test something that, by definition, cannot be seen? You cannot point a telescope at the vacuum and watch quantum fields moving through space. You cannot place a camera inside empty space and record microscopic fluctuations. The very phenomena predicted by quantum field theory occur on scales so small and so brief that they lie far beyond the reach of ordinary observation. For a time, it seemed possible that the vacuum's hidden activity would remain forever beyond human measurement. Then physicists realized something important. Even if the vacuum itself couldn't be observed directly, its effects might be. Just as we cannot see the wind itself, but can watch leaves bend beneath its force, invisible quantum fields might leave subtle fingerprints on the world around them. The challenge was no longer to photograph the vacuum. The challenge was to detect the tiny influences it exerted on measurable reality. That shift transformed the search completely. Instead of looking for empty space itself, scientists began designing experiments capable of revealing its consequences. They searched for places where quantum theory predicted that the vacuum should behave slightly differently than classical physics expected. The effects would be extraordinarily small, far smaller than anything human senses could detect. But modern instruments were becoming precise enough to measure differences that once seemed impossible. For the first time, the question was no longer purely theoretical. The vacuum had entered the laboratory. What happened next surprised even many of the researchers involved. Again and again, experiments began uncovering tiny discrepancies that classical physics could not explain on its own. They weren't dramatic explosions or spectacular flashes of energy. They were subtle, almost invisible deviations, small enough to escape everyday notice, yet consistent enough to appear wherever quantum field theory predicted they should. One measurement became 2, 2 became 10. Over time, a pattern emerged that grew increasingly difficult to dismiss. By the late 20th century, the evidence had become impossible to ignore. The strange mathematics describing quantum fields wasn't merely producing elegant equations. It was making predictions that nature repeatedly confirmed with astonishing precision. The vacuum was no longer just a theoretical concept discussed in university lecture halls. It had become something whose influence could be measured, tested, and verified. Empty space was leaving measurable fingerprints across the universe. But among all of those experiments, one stood out because of how simple it appeared. No giant particle accelerator, no distant galaxy, no billion-dollar space telescope. Just two perfectly smooth metal plates placed unimaginably close together inside a vacuum. What happened between those plates would become one of the most remarkable demonstrations that empty space is not truly empty, and it would forever change the way physicists think about the vacuum. Imagine taking two perfectly flat metal plates and placing them inside one of the best vacuums ever created. Every trace of air is removed, dust is eliminated, heat is carefully controlled. The plates are positioned so close together that the gap separating them is thinner than a human hair by thousands of times. According to classical physics, almost nothing should happen. With no air between the plates and no visible particles pushing against them, they should simply remain where they are. The space separating them appears completely empty. But it isn't. As the distance between the plates becomes unimaginably small, something extraordinary begins to happen. Without anyone touching them, without magnets, without hidden mechanical forces, the plates experience a tiny attraction toward one another. The effect is incredibly weak, far too small to notice without extremely sensitive instruments, but it is real. Time after time, experiment after experiment, researchers measured the same unexpected force. Somehow, empty space itself appeared to be contributing to the motion of physical objects. At first glance, the result seems impossible. How can nothing push on anything? For decades, that question puzzled physicists. The answer proposed by quantum field theory was as surprising as the experiment itself. Even inside a vacuum, the quantum fields filling space are never perfectly still. Their constant microscopic fluctuations create a background of restless activity. When the two metal plates are brought extremely close together, they slightly restrict the ways those fields can fluctuate in the narrow gap between them. Outside the plates, the fields have more freedom. Inside the gap, they have less. That tiny imbalance produces a measurable force, gently pushing the plates toward each other. The idea sounds almost unbelievable because it challenges the way we instinctively think about emptiness. We tend to imagine a vacuum as a blank stage where nothing exists and nothing happens. But the Casimir effect suggests something profoundly different. Empty space behaves more like a physical medium than an absence. Change the conditions within the vacuum and the vacuum itself responds, not dramatically, not violently, but measurably. The emptiness is no longer passive. It reacts. What makes this experiment so remarkable isn't the size of the force. In practical terms, it is extraordinarily small. What matters is what that force represents. It demonstrates that the vacuum cannot always be treated as featureless nothingness. It possesses structure. It possesses measurable properties. And under carefully controlled conditions, those properties can influence the behavior of matter in ways that classical physics alone cannot explain. A concept that once existed only in abstract equations had revealed itself inside a laboratory. The Casimir effect also changed the conversation surrounding quantum field theory. Critics could no longer dismiss the vacuum as merely a convenient mathematical idea. The predictions weren't just internally consistent, they matched reality. Around the world, increasingly precise experiments continued refining the measurements, and the agreement with quantum theory became stronger. Each new result carried the same quiet message. The vacuum was real enough to leave fingerprints that instruments could detect, even if human senses never could. But the Casimir effect was only the beginning. Physicists soon realized that the vacuum wasn't influencing carefully designed laboratory experiments alone. It was subtly affecting the behavior of atoms themselves, shifting tiny energy levels in ways no classical theory could predict. The effect was so small that it remained hidden for years, yet once it was measured, it became another stunning confirmation that the emptiness surrounding every atom is anything but empty. And that discovery would reveal that the quantum vacuum isn't just present between galaxies. It is quietly shaping the matter that makes up you, me, and everything we see. If the Casimir effect proved that empty space can influence objects in a laboratory, physicists naturally began asking a much bigger question. Could the vacuum also influence the fundamental building blocks of matter itself? If quantum fields truly fill the entire universe, then they shouldn't stop at the edge of a laboratory experiment. They should surround every atom, every molecule, every planet, and every living cell. In theory, the vacuum should be interacting with reality everywhere. For years, that idea remained difficult to test. The predicted effects were unbelievably small, far beyond anything that early instruments could detect. Yet as experimental techniques improved, researchers began measuring atoms with extraordinary precision. They weren't looking for dramatic changes. They were searching for tiny differences between what classical physics predicted and what nature actually revealed. Those differences were almost unimaginably small, but in science, even the smallest discrepancy can point toward an entirely new understanding of reality. One of the most famous examples became known as the Lamb shift. When physicists carefully measured the energy levels inside hydrogen atoms, they discovered something unexpected. The electron wasn't behaving exactly the way older theories predicted. The difference was tiny, but it was real, and more importantly, it was repeatable. At first, the result was surprising. As more experiments confirmed it, physicists realized they weren't looking at a measurement error. They were seeing evidence that the quantum vacuum was subtly influencing the atom itself. According to quantum field theory, an electron never exists in complete isolation. Even in what appears to be empty space, it is constantly immersed in surrounding quantum fields. Those fields undergo tiny fluctuations, and although each individual fluctuation is incredibly small, their collective influence slightly alters the electron's behavior. The result is a minute shift in the atom's energy levels, the Lamb shift. The effect is so subtle that it has no noticeable impact on everyday life, yet it matches the predictions of quantum electrodynamics with astonishing precision. The vacuum wasn't just affecting empty space, it was quietly reshaping the behavior of matter itself. This was another turning point. The quantum vacuum was no longer an abstract concept living only in sophisticated mathematics or highly specialized experiments. Its influence could be detected within the simplest atom in the universe. That realization carried enormous implications. Every object you've ever touched is built from atoms. Every breath you take, every cell in your body, every mountain, every ocean, every distant star, all are composed of matter existing within these same quantum fields. The invisible framework we've been discussing isn't confined to the emptiness between galaxies. It surrounds and permeates everything. Taken together, the evidence painted a remarkably consistent picture. The Casimir effect revealed that changing the vacuum changes measurable forces. The Lamb shift revealed that the vacuum subtly influences the structure of atoms. Different experiments, different scales, different methods, yet they all pointed toward the same conclusion. Empty space behaves as a physical entity with measurable consequences. What humanity once dismissed as nothing had become one of the most thoroughly tested foundations of modern physics. And yet, despite all this evidence, one profound mystery remained untouched. We can measure the vacuum's effects. We can predict its behavior with extraordinary accuracy. We can build technologies based on those predictions. But we still don't know why the vacuum has the properties it does. Why do these quantum fields exist? Why do they possess the strengths they have? Why is the vacuum stable at all? These aren't minor details waiting to be filled in. They are among the deepest unanswered questions in all of physics. And pursuing those questions has led scientists to an astonishing possibility, one that suggests the universe we know may not exist in its most stable state. If that idea is true, then empty space isn't merely mysterious. It may also be dangerously fragile. Everything we've explored so far has changed the way we think about empty space. We've seen that the vacuum isn't truly empty. We've discovered that invisible quantum fields fill the universe, that those fields can never become perfectly still, and that their effects can be measured with astonishing precision. But all of those discoveries lead to a far more profound question. What if empty space didn't merely shape the universe? What if it helped create it? For centuries, the story of the cosmos seemed straightforward. Nearly 14 billion years ago, the universe began in an event we call the Big Bang. Matter formed, stars ignited, galaxies slowly emerged from the darkness. It was a powerful narrative, but it left several mysteries unanswered. Why is the universe so remarkably uniform in every direction? Why is space almost perfectly flat on the largest scales? And how did tiny clumps of matter eventually grow into the enormous galaxies we see today? The original Big Bang picture struggled to answer all of these questions at once. During the late 20th century, physicists began exploring a bold new possibility. Perhaps in the earliest fraction of a second after the Big Bang, the universe experienced a period of unimaginably rapid expansion. Not an ordinary explosion through space, but an expansion of space itself. In less than the blink of an eye, far less than a trillionth of a second, the cosmos may have expanded by an almost inconceivable amount. This idea became known as cosmic inflation, and it transformed modern cosmology. At first, inflation sounded almost too extraordinary to be true. Yet it offered elegant explanations for several of the universe's biggest puzzles. Regions of space that seem impossibly similar today could once have been close enough to share the same physical conditions before inflation stretched them unimaginably far apart. The large-scale smoothness of the cosmos, which had puzzled astronomers for decades, suddenly became much easier to understand. A theory that once seemed wildly speculative began matching observations with remarkable success. But inflation carried an even more astonishing implication. If space itself expanded at such incredible speed, then the tiny quantum fluctuations we've been discussing throughout this documentary wouldn't have remained tiny. They would have been stretched across the growing universe, transforming microscopic irregularities into the seeds from which galaxies, stars, planets, and eventually life itself could form. Think about what that means. The largest structures in the observable universe may trace their origins to the smallest quantum fluctuations imaginable. Every galaxy scattered across the night sky, every cluster of stars, every planet, and every person who has ever lived may ultimately owe their existence to subtle fluctuations that once flickered through the quantum vacuum. If that picture is correct, then empty space didn't simply witness the birth of the universe. It helped write the blueprint. Imagine watching the universe less than a trillionth of a second after its beginning. There are no stars to illuminate the darkness, no galaxies stretching across space, no planets, no atoms, and no familiar structures of any kind. The universe is astonishingly small, unimaginably hot, and expanding at a rate that defies ordinary intuition. Yet hidden within that newborn cosmos are tiny irregularities, minute quantum fluctuations scattered throughout the vacuum. On their own, they are almost meaningless. They are smaller than anything human language can comfortably describe. Under normal circumstances, those fluctuations would have remained microscopic forever. But during cosmic inflation, something extraordinary happened. As space itself expanded at an unimaginable rate, those tiny fluctuations expanded with it. Ripples that once existed only on quantum scales were stretched across vast regions of the growing universe. What began as almost imperceptible variations in the quantum fields became slight differences in the density of matter and energy spread throughout the young cosmos. The differences were incredibly small, only a few parts in 100,000, but they were enough. Gravity would spend the next billions of years amplifying those tiny imperfections into something magnificent. Where matter was ever so slightly denser, gravity pulled in more matter. As more material accumulated, the gravitational pull became stronger, attracting still more gas and dust. Over immense stretches of time, those small overdense regions collapsed into the first stars. Stars gathered into galaxies. Galaxies assembled into clusters, and clusters connected through enormous filaments to form the vast cosmic web that spans the observable universe. The breathtaking structure revealed by our most powerful telescopes may have begun as nothing more than microscopic fluctuations in the quantum vacuum. That idea is difficult to comprehend because it connects two extremes of reality that seem completely unrelated. On one side is the quantum world, where events unfold on scales far smaller than atoms. On the other is the observable universe, stretching across billions of light years and containing hundreds of billions of galaxies. Yet modern cosmology suggests these two realms are inseparably linked. The largest structures we can observe may be the amplified echoes of the smallest fluctuations nature allows. Remarkably, this isn't just a beautiful story, it is supported by observation. When astronomers study the cosmic microwave background, the faint afterglow of the Big Bang, they find tiny temperature variations spread across the sky. Those subtle patterns match the predictions made by inflationary cosmology with extraordinary precision. They represent a snapshot of the universe when it was only about 380,000 years old, preserving the seeds from which galaxies would later emerge. In a very real sense, we can still observe the fingerprints of those ancient quantum fluctuations, frozen into the oldest light in the universe. Pause for a moment and consider the scale of that idea. The atoms in your body were forged inside ancient stars. Those stars formed inside galaxies. Those galaxies grew from slight variations in the early universe. And according to our best understanding of modern physics, those variations originated from tiny fluctuations within quantum fields, filling what we casually call empty space. The emptiness between the stars is no longer just the backdrop of the cosmic story. It may be the reason the story exists at all. But as extraordinary as that conclusion sounds, it leaves us with a deeper mystery than ever before. If the vacuum helped shape the universe we see today, could it also destroy it? That question has led physicists to one of the most unsettling possibilities ever proposed, a possibility suggesting that the very fabric of empty space may not be as permanent as it appears. And if that's true, then the greatest danger in the universe isn't hiding inside a black hole or a distant galaxy. It may already be all around us. If the theory of cosmic inflation is correct, then the universe carries a memory of its earliest moments. Not a memory stored in words or images, not a record hidden inside distant galaxies. A memory written into the very structure of space itself. Every galaxy scattered across the night sky, every enormous cluster spanning millions of light years, and every vast cosmic void separating them, may ultimately trace its origins back to fluctuations that existed when the universe was less than a fraction of a second old. Those fluctuations weren't erased as the cosmos expanded. They were stretched, amplified, and preserved, becoming the blueprint from which all large-scale structure eventually emerged. This is one of the most remarkable ideas in modern science. Normally, we think of the universe as constantly changing. Stars are born and die. Galaxies collide, black holes consume matter, entire solar systems evolve over billions of years. Yet beneath all of those dramatic events lies a deeper pattern established almost at the beginning of time. The universe didn't simply grow larger, it grew according to instructions encoded within the quantum vacuum itself. Modern telescopes allow us to see those instructions indirectly. When astronomers map the distribution of galaxies across billions of light years, they don't find a random scattering of matter. Instead, they discover an immense network of interconnected filaments surrounding gigantic regions of almost perfect emptiness. This structure, the cosmic web, is precisely the kind of pattern expected if today's galaxies evolved from tiny fluctuations stretched across the infant universe during inflation. The implication is breathtaking. Everything we recognize as the visible universe may owe its existence to quantum events so small that they occurred far beyond the limits of ordinary human experience. In other words, the largest things we know appear to have been shaped by the smallest things nature allows. By itself, that conclusion would already rank among the greatest discoveries in scientific history. But it also reveals something even more profound. Empty space is not merely where the universe exists. It has influenced how the universe evolved. From the first fraction of a second after the Big Bang to the formation of galaxies billions of years later, the vacuum has remained an active participant in the cosmic story. It is present between every star, inside every atom, and across every light year separating one galaxy from another. Wherever space exists, the quantum fields filling that space exist as well. And yet, despite everything we've learned, one environment continues to push those fields to their absolute limits. A place where gravity becomes so extreme that space and time themselves begin to break down. A place where two of physics' greatest theories, quantum mechanics and general relativity, collide. A place where empty space may behave in ways unlike anywhere else in the universe. Black holes. Because if there's anywhere the true nature of the quantum vacuum is exposed, it's at the edge of a black hole. There are places in the universe where our understanding of reality begins to fail. Black holes are one of them. On the surface, a black hole sounds simple. It is a region of space where gravity has become so strong that nothing, no matter, no light, no signal, can escape once it crosses a boundary known as the event horizon. But that simple definition hides something far more profound. A black hole is not just an object in space. It is a region where space itself is stretched, compressed, and distorted to an extreme degree. To understand why this matters, imagine slowly approaching a black hole. From far away, it might look like an ordinary dark sphere against the backdrop of stars. But as you get closer, something strange begins to happen. The rules that feel stable everywhere else in the universe start to behave differently. Time begins to slow down relative to distant observers. Light becomes stretched and redshifted. Space itself appears to deepen, as if reality is being pulled into something it cannot resist. At the edge of the event horizon, these effects reach their limit. From the outside perspective, an object falling toward a black hole appears to freeze in time, never quite crossing the boundary. But from the object's own perspective, the fall continues without interruption. This strange mismatch between viewpoints is not just a curiosity of relativity. It reveals something deeper about the nature of space and time themselves. They are not fixed backgrounds. They are dynamic, flexible, and capable of extreme distortion under the influence of gravity. Now combine this with everything we've learned about quantum fields. If empty space is filled with invisible fields that can never become perfectly still, then those fields must also exist near black holes. But near the event horizon, something extraordinary happens. The structure of spacetime becomes so distorted that even the behavior of quantum fields begins to change in ways that cannot happen anywhere else in the universe. This is where two of the greatest theories in physics meet and begin to conflict. General relativity describes gravity as the curvature of spacetime itself. Quantum field theory describes reality as a network of fluctuating fields filling that spacetime. Both theories are incredibly successful on their own. But inside and around black holes, they are forced to operate under conditions neither was originally designed to handle. The result is not a smooth merger of ideas, but a tension, one that hints at something deeper waiting to be discovered. Because if quantum fields are always fluctuating, and spacetime itself is being stretched to extremes, then something unexpected should occur at the boundary of a black hole. The vacuum should not remain silent there. It should respond to the curvature of space in ways that reveal its quantum nature more clearly than anywhere else. And this is exactly where one of the most astonishing predictions in physics emerges. A prediction that suggests black holes are not completely black. They are not eternal. And they are not truly silent. They are slowly changing in ways that no one expected. For most of modern history, black holes were considered the ultimate dead ends of the universe. Anything that crossed the event horizon was thought to be lost forever, trapped in a region from which nothing could ever return. Not even light, not even information. A black hole was not just dark, it was absolute darkness made permanent, the final state of matter, the final silence of physics. But in the 1970s, something remarkable changed that picture. When physicists began applying quantum field theory to the region just outside a black hole's event horizon, they discovered a result that seemed almost impossible to believe. According to the mathematics, the vacuum near a black hole is not completely calm. The extreme curvature of spacetime affects the quantum fields in a subtle but profound way. What appears to one observer as empty space may appear to another as a region where particle-like effects begin to emerge. At first, this sounds like a contradiction. How can nothing produce something? How can a region defined by the absence of escape begin to show signs of activity? The answer lies in the way quantum fields behave when spacetime itself is being stretched and distorted. Near the event horizon, the definition of what counts as a particle becomes dependent on perspective. Different observers moving under different gravitational conditions do not agree on what empty truly means. From this insight came one of the most extraordinary predictions in theoretical physics. A black hole is not completely black. Instead, it can very slowly emit a faint form of radiation. This phenomenon is now known as Hawking radiation. According to the theory, pairs of quantum fluctuations can briefly appear near the event horizon. In normal space, these fluctuations would quickly cancel out and disappear without consequence. But near a black hole, something different can happen. One member of the pair can fall into the black hole while the other escapes into space. To a distant observer, it appears as if the black hole is emitting particles. Over vast periods of time, this process causes the black hole to lose energy. The effect is incredibly small. For astrophysical black holes, the kind formed by collapsing stars, It is so weak that it is practically impossible to detect with current technology. A black hole many times the mass of our Sun would take far longer than the current age of the universe to evaporate significantly. And yet, despite its smallness, the implication is enormous. Because if Hawking radiation is correct, then black holes are not eternal. They are slowly shrinking. They are slowly leaking energy. And given enough time, they will eventually disappear entirely. This realization fundamentally changed how physicists think about black holes. They are no longer viewed as perfect cosmic prisons. Instead, they are dynamic objects, slowly evolving under the combined influence of gravity and quantum mechanics. The vacuum around them is not passive, it is actively participating in their evolution. But this leads to an even deeper and more disturbing question. If black holes can eventually evaporate, what happens to everything that fell into them? Does information disappear forever? Or does it somehow survive in a form we do not yet understand? That question opens one of the most controversial and unresolved debates in all of modern physics. And it forces us to confront a possibility even more unsettling than black holes themselves. Because if information can be destroyed in the universe, then something very fundamental about reality may be incomplete. And that is where the mystery of black holes stops being about astronomy and starts becoming a crisis in physics itself. At first, Hawking radiation seemed like the final word on black holes, a clean, elegant result from quantum fields theory applied to curved spacetime. Black holes are not eternal, they slowly lose energy. Over unimaginable timescales, they can evaporate completely. It was a beautiful conclusion, one that brought quantum physics and general relativity closer together than ever before. But beauty in physics does not always mean completeness. Almost immediately, a deeper problem emerged. If a black hole can evaporate entirely, then what happens to the information about everything that fell into it? Every particle that crossed the event horizon carried with it specific physical information, its mass, its spin, its quantum state. In classical physics, that information is never truly destroyed. It can be transformed, scrambled, hidden, but in principle, it always remains part of the universe's overall record. But Hawking radiation seemed to suggest something far more troubling. The radiation emitted by a black hole appears completely random. It carries energy, yes, but not the detailed information about what originally fell in. As the black hole slowly shrinks and eventually disappears, it seems as if all the information about its contents is lost forever. That conclusion creates a direct conflict with one of the deepest principles in quantum physics. That information about a closed system should never be destroyed. This is not a small technical disagreement. It is a fundamental clash between two pillars of modern physics. On one side is general relativity, which describes black holes as smooth, predictable distortions of spacetime. On the other is quantum mechanics, which insists that information is preserved in the evolution of every physical system. Hawking radiation sits uncomfortably between them, forcing both theories into a situation neither was fully designed to handle. Physicists have spent decades trying to resolve this paradox. Some believe the information is somehow encoded in the radiation itself, in a way too subtle for us to currently decode. Others suggest it might remain stored on the surface of the event horizon, stretched and scrambled in a holographic form. Some even propose that our understanding of spacetime itself must change at a fundamental level to resolve the contradiction. But despite all these ideas, no single explanation has been universally accepted. The black hole information problem remains one of the most important unsolved questions in physics today. And that uncertainty has an unsettling implication. If we do not fully understand what happens to information inside black holes, then we may also not fully understand what happens to information in the fabric of reality itself. Because black holes are not just exotic objects at the edge of the universe. They are extreme laboratories where the deepest laws of physics are tested to their limits. And when those laws begin to break down, they do not do so quietly. They point towards something deeper, something still hidden, something that may finally explain what empty space truly is at its most fundamental level. And that is where the next question begins. Not about black holes, not about stars, but about the vacuum itself when it is pushed beyond stability. Because if empty space is not perfectly stable, then even reality itself might be temporary. For most of modern physics, empty space is assumed to be stable. It may be strange, it may be active at the quantum level, but it is fundamentally reliable. The vacuum is the stage on which everything else exists. Stars form in it. Galaxies evolve within it. Time and space themselves are defined through it. No matter how strange quantum fluctuations become, the vacuum itself is expected to remain unchanged. But there is a more unsettling possibility, one that emerges naturally from the same quantum field theory that has explained so much of the universe so far. What if the vacuum is not the lowest possible state of reality? What if it only appears stable because we are trapped in it? In quantum physics, systems often have multiple possible energy states. Some are stable, others are only temporarily stable, like a ball resting in a shallow valley that looks safe, but is not the lowest point in the landscape. Given enough disturbance, even a seemingly stable state can transition into a deeper, more stable configuration. This idea becomes far more significant when applied to the vacuum of space itself. Because if quantum fields define everything we see, then the vacuum is simply the lowest energy arrangement of those fields. But there is no guarantee that this lowest state is truly the absolute lowest possible state. It may be what physicists call a false vacuum, a state that appears stable, but is not the most stable configuration allowed by nature. At first, this sounds like an abstract mathematical possibility, something that might exist in equations but not in reality. However, modern particle physics suggests that the vacuum state of our universe depends delicately on the properties of fundamental fields, including those associated with particles like the Higgs boson. When scientists analyze these values, they find something surprising. Under certain conditions, the vacuum we occupy may not be perfectly stable after all. Instead, it may be metastable, a temporary equilibrium, a cosmic state that can, in principle, transition into something lower. And if that transition were ever triggered, the consequences would not be local. It would not be limited to a region of space or a single star system. It would not even be limited to a galaxy. It would affect everything. Because the vacuum is not just empty space. It is the structure that defines what particles are, what forces are, and even what laws of physics mean. A shift in the vacuum state would not rearrange matter inside the universe. It would rewrite the universe itself. But this is not something that happens easily. If false vacuum decay is possible, it would require conditions or fluctuations beyond anything we have observed. For all practical purposes, the vacuum appears stable. It has existed for billions of years without any sign of change. Every experiment we perform confirms the same underlying structure of reality. And yet the mathematics refuses to completely rule out the possibility. Which leaves us with a disturbing conclusion. The universe may be built on a foundation that is not truly permanent. And if that is true, then the emptiness surrounding everything we know is not just mysterious. It is potentially fragile. And somewhere in that fragility lies one of the most profound questions in all of physics. What happens if empty space itself changes? And more importantly, would we even see it coming? If a transition from a false vacuum to a lower energy state were ever to occur, it would not behave like any event we normally imagine in physics. There would be no explosion in the ordinary sense, no shockwave traveling through space in a conventional medium, no warning signal that something is about to happen. Instead, it would begin in a way that is almost impossible to visualize. A single point in space would shift into a more stable configuration of quantum fields. From that point, a new state of vacuum would begin to expand outward at the speed of light. To anything in its path, it would not appear as a moving object. It would not appear as energy traveling through space. It would appear as a fundamental change in reality itself. The laws governing particles, forces, and interactions would be different on the other side. Atoms might not form in the same way. Chemistry might not exist in any recognizable form. The very structure of matter could be altered at its most basic level. And because this transition would propagate at light speed, there would be no way to detect it in advance. No signal could outrun it. No observation could reveal it before it arrived. By the time it was visible, it would already be here. This is why physicists describe false vacuum decay not as a traditional catastrophe, but as a phased transition of the universe itself. It is not destruction in the conventional sense. It is replacement, one state of reality giving way to another. Inside the mathematics of quantum field theory, this process can be visualized as the formation of a bubble of true vacuum appearing within the false vacuum. Once formed, that bubble would expand, converting everything it encounters into the new vacuum state. Any matter inside the bubble would be instantly redefined by the new physical laws. Stars would not survive it. Planets would not survive it. Even spacetime itself would be restructured. What makes this idea so unsettling is not just its scale, but its inevitability if the conditions are right. If the vacuum is truly metastable, then the transition does not require an external cause in the way everyday events do. In quantum physics, transitions can occur spontaneously, driven by fluctuations in the underlying fields. Rare as they may be, they are not forbidden. However, there is an important point that must be understood clearly. There is no evidence that such a transition is happening. There is no sign that the universe is unstable in any immediate sense. All current measurements suggest that if we are in a false vacuum, its lifetime is far longer than the age of the universe. But the fact that this possibility cannot be completely excluded is what makes it scientifically significant. Because it reveals something profound about our understanding of reality. The universe we inhabit may not be guaranteed to remain in its current form forever. And even more unsettling, it may not have always been this way. Somewhere in the distant past, or perhaps in some deeper layer of physics beyond what we currently understand, there may exist a more fundamental state of reality, a state from which everything we know emerged. And if that is true, then the question is no longer whether the vacuum can change. The question becomes why it hasn't already changed. And that leads us directly into the next frontier of this mystery. Because if our vacuum is only one possible state among many, then understanding why this particular state exists at all becomes one of the most important questions in physics. A question that takes us beyond stability, beyond particles, and even beyond spacetime itself. Into the deeper structure of reality. For most of human history, the night sky appeared eternal. Stars rose and set. Constellations shifted slowly across generations, but on human timescales, the universe felt permanent. Even when science revealed that stars are born and eventually die, the sheer timescales involved made the cosmos feel effectively unchanging. It was easy to imagine that, for all practical purposes, the universe would continue much as it is now, indefinitely. But modern cosmology has shown that the universe is not static. It is evolving, expanding, changing. And that change has a direction. The discovery that the expansion of the universe is accelerating introduced a completely new vision of the cosmic future. Instead of slowing down under the influence of gravity, galaxies are moving away from each other faster and faster. Over vast stretches of time, this expansion will reshape everything we can see. As space continues to expand, distant galaxies will gradually disappear beyond our observable horizon. Not because they are destroyed, but because the space between us and them grows faster than light can bridge. The night sky will become darker, not suddenly, but slowly over billions and trillions of years. Future civilizations, if they exist, may look into the cosmos and see far fewer galaxies than we do today. Eventually, only the gravitationally bound structures will remain visible. Galaxies like our own Milky Way will remain intact for a long time, held together by their internal gravity. But even within those structures, change will continue. Stars will burn out one by one. New star formation will slow as the raw material for stellar birth is consumed. Over immense timescales, the universe will transition from a bright, active cosmos into a colder, darker, and more isolated state. This is sometimes referred to as the heat death of the universe, not because everything becomes hot, but because energy becomes evenly distributed, making all processes that require differences in energy increasingly difficult to sustain. Without energy differences, there can be no stars, no chemistry, and no structured activity as we know it. It is a future defined not by dramatic destruction, but by gradual fading. And yet, even this slow cosmic ending assumes something important, that the vacuum itself remains unchanged. But everything we have learned so far in this documentary challenges that assumption. Because if empty space is not simply a passive backdrop, but an active physical entity governed by quantum fields, then it is not just matter and energy that evolve over time. It is the vacuum itself that defines how that evolution happens. And if the vacuum is connected to dark energy, as many modern theories suggest, then it may not simply be a silent witness to the expansion of the universe. It may be the reason that expansion is happening at all. Which leads to a profound realization. The fate of everything we see in the night sky may not depend only on stars, galaxies, or gravity. It may depend on the properties of empty space itself. And if that is true, then understanding the vacuum is not just a question of fundamental physics. It is a question about the ultimate future of everything that exists. But even that may not be the deepest implication. Because once you accept that empty space can shape the fate of the universe, another possibility begins to emerge. One that asks whether the laws we take for granted are truly fixed, or whether they are simply one expression of something even more fundamental, still waiting to be understood. And that question takes us beyond the end of time as we currently imagine it, into the possibility that reality itself may have deeper layers than anything we have yet discovered. The further physicists look into the future of the universe, the more their predictions depend on one critical unknown: the nature of empty space itself. If the expansion of the universe is driven by something like vacuum energy or a related property of quantum fields, then even small changes in that underlying structure could completely alter the long-term fate of everything we observe. A slight difference in the energy density of the vacuum could determine whether galaxies remain gravitationally bound, whether expansion continues forever, or whether it eventually slows and reverses in ways we cannot currently rule out. This is what makes dark energy so unsettling in modern cosmology. It is not just a name for an observed effect. It is a placeholder for something we do not yet understand. We can measure its influence on the expansion of space. We can map its effects across billions of light years, but we do not yet know what it actually is. And because of that, the future of the universe is not fully written. In science, we often assume that once the present state of the universe is known, its future can be calculated. This is true in many physical systems. But when the dominant influence on cosmic expansion comes from an unknown property of the vacuum, that certainty begins to weaken. The equations still work, but the deeper meaning behind them becomes less clear. This is not just a technical gap in knowledge. It is a fundamental limitation. We are trying to predict the fate of everything based on an ingredient we do not yet fully understand. And that leads to a striking realization. The vacuum is no longer just a component of physics that needs to be explained. It has become the central uncertainty in our understanding of everything from the birth of the universe to its ultimate fate. Every major cosmic scenario, eternal expansion, eventual collapse, slow heat death, or something even more exotic, depends on how the vacuum behaves over unimaginable timescales. If its properties are truly constant, one set of outcomes emerges. If they evolve even slightly, an entirely different cosmic history becomes possible. This means that the emptiness between galaxies is not just part of the universe's structure. It is part of its uncertainty. And perhaps most importantly, it may be the bridge between what we can currently explain and what we cannot yet even imagine. Because if the vacuum is responsible for shaping both the origin and the fate of the cosmos, then it cannot simply be treated as a background detail in physics. It must be part of the deeper mechanism from which reality itself emerges. And that brings us to the final and most unsettling shift in perspective so far. A shift that moves beyond cosmology, beyond quantum fields, beyond even spacetime itself. Because at that point, the question is no longer what empty space does. The question becomes what empty space actually is. For most of modern physics, space and time are treated as the stage on which everything happens. Matter moves through space. Energy evolves over time. Forces act across distances defined by space itself. Even in Einstein's theory of relativity, space-time is not just a passive background. It is a dynamic structure that can bend, stretch, and curve under the influence of matter and energy. But there is a deeper question that modern physics has not fully answered. What if space-time itself is not fundamental? What if space and time are not the foundation of reality, but something that emerges from a deeper layer we cannot yet directly observe? This idea may sound abstract, but it appears naturally when physicists try to combine quantum mechanics and gravity. In quantum theory, everything is described in terms of fields and probabilities. In general relativity, everything is described in terms of geometry and curvature. Both frameworks are extremely successful in their own domains, yet when pushed to extreme conditions, inside black holes or near the beginning of the universe, they begin to resist unification. This tension has led some researchers to suspect that both spacetime and matter might be emergent phenomena. In other words, they may not be the most basic ingredients of reality. Instead, they could arise from something more fundamental, just as temperature arises from the motion of microscopic particles, even though temperature itself is not a fundamental substance. If that analogy is correct, then space might be a large-scale effect of something happening at a deeper level of reality. And if space is not fundamental, then the vacuum is not just empty space. It is the expression of whatever lies beneath space itself. This is where modern theoretical physics begins to explore ideas such as quantum information, entanglement, and the possibility that spacetime geometry is linked to patterns of connections between more basic entities. In some interpretations, what we perceive as distance may actually arise from how strongly underlying components of reality are related to each other. Where connections are dense, space appears close. Where they are weak, space appears far. If such ideas are correct, then empty space is not simply the absence of objects. It is the structure created by relationships we do not yet fully understand. And that would completely change how we think about the vacuum. Because the vacuum would no longer be a thing inside the universe. It would be what defines the universe itself. Every particle, every force, every law of physics would then be expressions of this deeper structure, with spacetime emerging as a kind of large-scale pattern from an underlying quantum reality. This does not mean we have proven such a picture. We have not. These ideas remain at the frontier of theoretical physics, still being developed and tested. But what makes them important is not certainty. It is direction. Because again and again, physics has shown that what we once thought was fundamental often turns out to be emergent. Solid objects are made of atoms. Atoms are made of quantum fields. Fields themselves may be manifestations of something even deeper. And each step in that chain has moved us closer to a reality that is less intuitive, but more unified. Which brings us to a profound possibility. If space, time, and matter are all emergent, then the vacuum is not empty at all in any classical sense. It is the most complete expression of the underlying structure of reality. And everything we have called nothing may actually be the most important something in existence. But even this may not be the end of the story. Because if reality has layers beneath spacetime, then the question is no longer what those layers are. The question becomes, how many layers there are still left to discover? There is a point in every scientific journey where observation stops being enough. Not because the instruments fail, but because the questions begin to reach beyond what can be directly tested. Modern physics has already crossed many such boundaries. We have learned to describe particles that cannot be seen directly. We have built theories that depend on entities that exist only through their effects. We have even inferred the structure of the early universe from faint patterns of radiation still traveling through space today. And yet, when it comes to the deepest structure of reality, we are still working at the edge of what is currently measurable. The vacuum is a perfect example of this boundary. We can measure its influence. We can detect its subtle effects in laboratory experiments and cosmological observations. We can build mathematical frameworks that describe it with extraordinary precision. But we cannot directly access the underlying mechanism that gives rise to it. This creates a strange situation in modern physics. On one hand, our theories are incredibly successful. They predict experimental results with accuracy that would have seemed impossible a century ago. On the other hand, the deeper meaning behind those theories remains unclear. We know how the vacuum behaves, but not why it behaves that way. And this gap between prediction and understanding is where some of the most important questions in science now live. Why do quantum fields exist at all? Why do they have the values they do? Why is the vacuum structured in a way that allows matter, energy, and spacetime to emerge in the first place? These are not questions about missing details, they are questions about foundations. And history suggests something important about questions like these. Every time physics has reached a similar boundary, what looked like the end of understanding turned out to be the beginning of a deeper layer of reality. What once seemed like fundamental forces turned out to be different manifestations of a unified interaction. What once seemed like solid matter turned out to be mostly empty space filled with quantum fields. What once seemed like empty space itself now appears to be an active, structured, and possibly emergent phenomenon. Each step has revealed that reality is less intuitive, but more interconnected than we previously believed. Which raises a possibility that is difficult to ignore. If the vacuum is not fully understood, and spacetime itself may not be fundamental, then we may still be far from the deepest layer of reality. And if that is true, then what we currently call the laws of physics may not be final descriptions. They may be effective descriptions, accurate within a certain level of reality, but emerging from something deeper we have not yet reached. This does not make current physics wrong, far from it. It means current physics is extraordinarily successful within its domain, but it may not be the final word. And that brings us to a quiet but profound realization. The universe may be far richer than the framework we currently use to describe it. And empty space, the thing we once thought contained nothing at all, may be the clearest hint that there is more to discover than we ever expected. Because the more deeply we look into the vacuum, the more it stops behaving like emptiness. And the more it begins to resemble something we are only beginning to understand. Which leads us to the final question of this journey. Not what lies inside the vacuum. Not how it behaves. But why anything exists in a form we can even begin to describe. And that question brings everything back to where we started. To the simplest idea in the universe. Nothing. After everything we have explored, the quantum fields, the fluctuations of empty space, the structure of spacetime itself, we arrive back at the question that started it all. What is nothing? At first it seemed like the simplest idea imaginable. Nothing was the absence of everything. No matter, no energy, no space, no time, a perfect void where existence itself had been removed. For centuries, that definition was enough. It allowed us to build our earliest understanding of reality without questioning what lay beneath it. But as physics advanced, that simple idea began to dissolve. The vacuum stopped behaving like emptiness. Space revealed itself as something active. Quantum fields filled what we once called nothing, constantly fluctuating even in the absence of matter. Black holes showed that spacetime itself can stretch, bend, and eventually evaporate. And modern cosmology suggested that even the structure of the universe on the largest scales may have been shaped by microscopic variations in what we thought was empty space. Each discovery did the same thing in a different way. It removed another layer from the illusion of nothingness. And yet, the more we removed, the more something remained. This is the paradox at the heart of modern physics. The closer we come to eliminating everything, the more structure appears beneath what is left. The vacuum is not a blank absence. It is a dynamic system with properties, behavior, and consequences that extend across the entire cosmos. Even our most advanced theories now suggest that what we call empty space is not truly empty in any classical sense. It is filled with fields. Those fields are governed by laws, and those laws may themselves emerge from an even deeper level of reality that we are only beginning to explore. Which leads to a difficult conclusion. Perhaps nothing was never a physical state of the universe at all. Perhaps it was only a limit of human imagination. Because every time we have tried to define nothing precisely, nature has responded by revealing something underneath it. Something invisible. Something structured. Something real. And this brings us to the final stage of the journey. If nothing, as we once understood it, does not exist, then the question is no longer what remains when everything is removed. The question becomes why there was something to begin with at all. And at that point, physics reaches its edge. Not because the universe stops, but because explanation itself begins to run out of language. In the end, the universe does not give us a final answer. It gives us something more unsettling. It shows us that every layer we uncover reveals another layer beneath it. Every definition of nothing collapses into something more complex. Every attempt to find a final boundary of reality ends with that boundary dissolving into something deeper. We once believed the universe was made of matter. Then we discovered atoms. Then particles, then fields, then spacetime itself began to look like something that might not be fundamental at all. And now even the vacuum, the closest thing to nothing we can imagine, refuses to be empty. It has structure. It has behavior. It has consequences that reach across the entire cosmos. So what does that leave us with? Not a universe built on solid ground, but one built on something far less intuitive. A reality where empty space is not empty, where nothing is not nothing, and where even the absence of everything still has rules. The most uncomfortable part is not what we have discovered. It is what we have lost. The simple picture of reality, of a universe sitting inside a silent void, no longer exists. In its place is something far stranger. A cosmos where the void is active, where emptiness is dynamic, and where the difference between something and nothing begins to fade at the deepest level we can probe. And yet, even this may not be the final picture. Because every answer we have found so far has carried the same hidden message. We are not reaching the end of understanding. We are reaching the edge of a much larger unknown. So when we ask again, one last time, what is nothing? The honest answer is no longer a definition. It is a realization that what we once called nothing was never truly empty. It was only unfamiliar. And somewhere inside that unfamiliarity, hidden in the quiet structure of space itself, the universe continues to whisper a truth we are still trying to understand. Not that there is nothing, but that what exists is far deeper than we ever expected. And as the last thought settles, the question does not disappear. It simply changes form. Not, what is nothing? But, why does anything exist at all, when nothing was ever truly an option?